June 2018, paper 6, variant 1. Question 1. The volume of dilute nitric acid that reacts with 25 centimeter cube of aqueous potassium hydroxide can be found by titration using the apparatus shown. So this question is about the titration between nitric acid and potassium hydroxide. A, complete the box to name the apparatus. This is a burette, of course. B, name a suitable indicator that could be used, methyl orange or litmus. You can use something called thymolphthalene, but it's not a common indicator. Phenolphthalein is not that good of a choice because phenolphthalein gives colorless in the neutral and in the acidic solutions, so it could be confusing. Also, universal indicator is not a good indicator in titration because it gives a range of colors that might confuse the person doing the titration when trying to detect the endpoint. The student did the titration 4 times and recorded the volume of dilute nitric acid needed, which is called sometimes the titer volume. CI, which one of the results is anomalous? Anomalous means that it's odd. It's not going with the rest of the results. The result that something seems wrong in it. It's result number 2, of course, 18.9 centimeter cube. Since 1 is 18.1, result 3 is 18.3, result 4 is 18.2. The only one that went way beyond the endpoint was 2. Suggest what might have caused this result to be anomalous. There are 2 possible reasons. The person doing the titration might have went past the endpoint, okay? He didn't recognize the color change and have passed the endpoint and added more nitric acid. That's why the volume of nitric acid in experiment 2 was very high. Or he added more than 25 centimeter cube of potassium hydroxide in the conical flask at the beginning of the experiment. You see the 25 centimeter cube needed around 18.1 or 18.2 centimeter cube to be neutralized. The reason that he might have needed that large volume in experiment 2 is that he maybe he added more than 25 centimeter cube in the conical flask at the beginning, and that's why he required that large volume of nitric acid. III, use the other results to calculate the average volume of dilute nitric acid that reacted with the aqueous potassium hydroxide, okay? The other results means you cross out this result and you get the average between these 3 results. Okay, so the average is 18.1 plus 18.2 plus 18.3 over 3. It's the normal way we get average for any results. We add the results divided by their number. The result will be 18.2 centimeter cubed, and take care the unit has a mark. D, the equation for the reaction taking place in the titration is shown. Nitric acid plus potassium hydroxide will give me potassium nitrate and water. The student concluded that the aqueous potassium hydroxide was more concentrated than the dilute nitric acid. Explain whether or not the student's conclusion was correct. Okay, we needed an average of 18.2 centimeter cube of nitric acid to neutralize 25 centimeter cube of potassium hydroxide. This means that the nitric acid is more concentrated, not what the student said, because we needed a smaller volume of nitric acid to neutralize a larger volume of potassium hydroxide. Okay, so the one that was more concentrated was nitric acid. So the student's assumption is not correct. This is a mark. Nitric acid was more concentrated because a smaller volume of acid was needed. Okay, this is the second mark. Question 2 is a very famous experiment of the reaction between aqueous sodium thiosulfate and dilute nitric acid. Okay, this reaction produces sulfur, which is a yellow solid, and sulfur builds up in the solution until it blocks the vision of the inspector, so he won't see the printed words on the printed sheet. The faster the rate, the faster the sulfur will build up in the conical flask, and the faster the observer will not be able to see the printed words. He repeated the experiment several times, every time changing the concentration of sodium thiosulfate, okay? So in experiment 2, he added 40 centimeter. In experiment 3, he added 35, 30, 10. Every time he's changing the volume of aqueous, the concentration of aqueous sodium thiosulfate. And of course, to change the concentration, you also need to change the volume of the water added, okay? So he compensates for the volume of thiosulfate that he removes by adding more water in order to dilute the solution. Then they gave you the results. Okay. The results are here: 0, the volume of distilled water, 0, 10, 15, 20, 40. Notice that always the volume of aqueous sodium thiosulfate plus the volume of distilled water must be equal to 50 centimeter cubed in order to make a fair test. Okay, so that the total volume of the solution is always the same. The time taken for the printed words to disappear from view: 27, 33, 45, 66, and 201 seconds. Remember to multiply the minutes with 60. Okay, this is the graph. Okay, this is not a perfect graph because drawing on a screen is not like drawing on a real graph paper. So excuse me if it's not as accurate as it should be. The blue one is the graph that you should go in CI. Okay. A smooth line means you use your hand. You never use a ruler unless he says a straight line. In CI, sorry, you should have drawn the graph in B. In CI, he's asking you to get the volume, sorry, the time needed for the printed words to disappear at 20 centimeter cube of aqueous sodium thiosulfate, and he wants you to show your working on the grid. The two lines are perpendicular to each other in black. These are the lines you must show on the graph, and the volume at 20 centimeter. The time needed will be around 129 seconds. Okay, it differs from graph to graph slightly. Then double I, he just gave you a formula to compensate in. Rate of reaction equals 1 over time taken. He wants you to calculate the rate of the reaction using your answer from CI. Okay, you will take your answer from CI and put it in this formula. So if your answer is like me, 129, it will be 1 over 129. And it's also good to write the answer in decimals. Always in chemistry, take any answer to 3 significant figures. DI, in which experiment was the rate of the reaction greatest? Experiment 1. Explain why. Because experiment 1 had the highest concentration of sodium thiosulfate, so more particles per unit volume and more frequent collisions. The 2 marks are for more particles per unit volume and more frequent collisions. E, give the name of a more accurate piece of apparatus to measure volume than a measuring cylinder, burette or pipette, of course. F, suggest the effect on the results of using 100 centimeter cube conical flask instead of 250 centimeter cube conical flask. Okay. In this experiment, we are recording the time needed for the printed sheet to disappear from below the conical flask. If this is a 250 centimeter cubed flask, and we repeated the same experiment, using a 100 centimeter cube conical flask, which of course has a lower surface area, the solution in the 250 centimeter cube flask, okay, will have a shorter depth. It will not be as deep as in the 100 centimeter cubed conical flask. The more the depth of the solution, the smaller the surface area of it, and therefore sulfur will build up here faster. It doesn't have a large surface area to build up through because the depth of the solution is higher here. And since that in the 100 centimeter cube, sulfur will build up faster than in the 250 that has a large surface area to cover, this means that the time needed in the 100 centimeter cube experiment will be lower. The time for the crust to disappear would be shorter, okay, when you use the 100 centimeter cube conical flask, because the depth of the solution is greater. As the depth increases, the surface area is smaller. Cations and anions question 3. You have 2 substances, solution A, okay, and solid B were analyzed. Test on solution A, he just divided it into 3 equal portions. The first test, he measured the pH, pH 1. This means that we have a strong acid. Then in test 2, magnesium ribbon was added to the second portion, effervescence, okay? An acid with magnesium, this means that the gas is hydrogen. Acid plus metal gives salt and hydrogen. The gas produced was tested, pop sound, this is a confirmation for hydrogen gas. Test number 3, dilute nitric acid and aqueous barium nitrate were added to the portion. You must remember that the barium nitrate is the test for sulfate anion, and it is present since barium gave a positive result, which is white precipitate. Identify the gas produced in test 2, it's hydrogen, of course. Identify the solution A. You've proved that sulfate is present, and you know that this is a strong acid. So since it's an acid with sulfate, it is sulfuric acid, okay? If you said sulfate only, you take 1 mark. Test on solid B, which is zinc carbonate. He already gave you the cation. So you tell yourself, I have the cation, which is zinc. I have the anion, which is carbonate. Dilute nitric acid was added to solid B. The gas produced was tested. Acid on a carbonate releases always carbon dioxide, which is tested by lime water, okay, which turns milky or goes cloudy. Then he's testing for the cation, the zinc, okay? Aqueous sodium hydroxide was added to the first portion of zinc nitrate. Zinc with anything gives white precipitate, and zinc with anything gives a white precipitate that is soluble in excess. By anything, I mean sodium hydroxide or aqueous ammonia. So the result here will be white precipitate soluble in excess, and the result here will be also white precipitate, which is soluble in excess. Okay, finally, the experimental design question, which was not very easy this time. Okay, potassium chloride is a salt that dissolves in water. So you know that now that it's a soluble salt. Okay, the solubility of a salt is the mass in grams of the salt that dissolves in 100 centimeter cubed of water at a particular temperature. Plan an investigation to determine the solubility of potassium chloride in water at 40 degrees Celsius. You're provided with a potassium chloride. You're provided with potassium chloride and common laboratory apparatus. Okay, so what does he want in this experiment? He tells you that the solubility of a salt is the maximum mass of the salt. Okay, assume this is the salt. The maximum mass of the salt that you can dissolve in 100 centimeter cubed of water at a certain temperature. And then he told you that the salt in the experiment will be potassium chloride, and that the temperature he wants to measure the solubility at is 40 degrees Celsius. So how can I know the maximum mass of solid that can dissolve inside 100 centimeter cube of water, the maximum mass of potassium chloride? There's a very simple way. You get 100 centimeter cubes of water in a beaker. You adjust the temperature at 40 degrees Celsius using a thermometer, and then you start adding solid potassium chloride until the solid is excess, or until no more solid dissolves. It remains at the bottom, okay? Now you know that the solution, that the water is saturated with potassium chloride. You just need to know how many grams are dissolved in this water. So first of all, you remove the excess potassium chloride by filtration. Okay, you remove the excess potassium chloride by filtration. Imagine with me that we successfully removed potassium chloride. This means that we now only have a solution of potassium chloride, a solution of 100 centimeter cube of water with potassium chloride dissolved in it. Okay, so imagine potassium chloride is dissolved in all this water. Now we need to know the mass of the solid dissolved in the water. The easiest way is by evaporation. Water will evaporate and the solid will remain at the bottom. We just need to get it and dry it and weigh it. Of course, do not wash it because this is a very soluble solid. It will dissolve again. So we just dry it between 2 filter papers and weigh it, and we've arrived at our goal. Okay, these are the 6 points. Every point is for a mark. Okay, every point is for a mark, and measuring cylinder also takes a mark. There's another method that you could use, which is the mass not used method. You could get a known mass of potassium chloride solid at the beginning, and you can start adding until no more dissolve, and then you can measure the mass remaining of the potassium chloride at the end, and you subtract the mass that you started with of the potassium chloride, and you subtract from it the mass that remained, and you will know by this way the mass of potassium chloride that dissolved. But I think that the method written is the better one and the easier one. This was June 2018 by Mr. Marco.